Hello, I'm Mr. McBrien. This is SPH3U, Sound Intensity. Ontario intends for grade 11 physics students to be able to explain natural phenomena with reference to the characteristics and properties of waves and analyze the effects that mechanical and sound waves have on society and the environment. We can talk about the energy in a given wave in terms of the amplitude of the vibration. And we can reconcile this with our idea of the amount of work done to displace the medium is proportional to the amplitude. And so the greater the displacement at the source, the more energy the wave is going to carry. So we can see on the left we have small amplitude associated with low energy and large amplitude corresponding to high energy. So the rate at which the energy is transported past a given area of the medium is known as intensity. And no big deal, intensity is energy over the area and the time. And that, of course, gives us the rate piece. Now, it's important that we differentiate this rate with the speed of the wave. This is the amount of energy per time unit. And of course we know that energy over time is power. And so we can extract out the energy over time term in intensity and say that intensity is power over area. And of course, if we take watts as the unit of power and square meters as the units of area, then we have watts per square meter. Now, as we well know, sound diminishes over distance. And as a wave carries its energy through a three-dimensional medium, the intensity of the wave is going to decrease with distance. We can rationalize this idea with the idea that a sound wave moves out in a spherical fashion and the area increases and thus the energy per unit area decreases. So our energy can't magically increase as the wave proceeds out from the source. So the energy remains constant, but the area is increasing. And we've got a few pictures here that can help us with this. So we have on the left our source. We have our source of the power, and it moves outward in a spherical fashion. And if we remember our formula for area of a sphere, we can say that the area is expanding outward proportional to r squared. And in our example, we can see at a distance of 1, our area is 1. At a distance of 2, we get 4 times the area, and at a distance of 3, we have 9 times the area. Okay, so what are we saying? We're saying the mathematical relationship between intensity and distance is an inverse square relationship. In other words, if the distance from the source is doubled, then the intensity is decreased by a factor of 4, or 2 squared. And if we plot that, if we plot the distance versus intensity, we can see if we normalize it at a distance of 1, we have an intensity of 1, and it drops off very quickly with the square of the distance. Okay, the good news though is that humans have extremely sensitive hearing. So the tiny groups of cells that are a lot like hairs called cilia in our ears are extremely effective detectors of changes in pressure. And so we can detect a sound wave with intensity as faint as 1 times 10 to the negative 12 watts per meter squared. That corresponds to a pressure wave in which the compression increases the air pressure by just 3.3 billionths of an atmosphere. An incredibly small signal. Now that small signal that is right at the edge of what we can hear is called the threshold of hearing. But we have tremendous dynamic range in our ears, and so the most intense sound we can hear is more than 1 billion times more intense than that. So if we tried to describe the intensity of sound on a linear scale, it would just be impossible to fathom. Instead, we view it on what's called a logarithmic scale. We talk about 10 times increases in intensity. What does that mean? Well, we can talk about it. Now. We have a decibel scale, and you may have heard of it, for describing the intensity of sound. So the way the decibel scale works, the threshold of hearing, which for an average person is again 1 times 10 to the negative 12 watts per square meter, is assigned a sound level of 0 decibels. And a sound 10 times more intense than that, say the sound of rustling leaves, is assigned a sound level of 10 decibels. Something 10 times as strong as that? Well, we assign that a sound level of 20 decibels. So the 0 is a placeholder, and the number in front of the 0 is the number of orders of magnitude, or 10 times values above the threshold of hearing. So if we have something 1,000 times more intense, then it has an intensity of 30, a sound level of 30 decibels. So we can look at relative intensities by just simply subtracting decibel levels and saying that it's 10 to the x times more intense. So let's illustrate this. A mosquito's buzz is often rated with a decibel rating of 40 decibels. Normal conversation, about 60 decibels. So how many times more intense is normal conversation compared to a mosquito's buzz? Well, we can subtract and get 20 decibels difference, which is 10 to the 2 or 100 times as loud. Let's take another example. Someone standing 1 meter away from a busy street measures the decibel level of the traffic to be 70 decibels. If they were 10 meters away from the traffic, what would the intensity be? What would the noise level be? Well, first we have to apply our concept of sound intensity being proportional to r squared. So we have to say to ourselves, since we're 10 times as far away, we're 10 squared diminished in intensity, or 1/100th as intense. So knowing that it's 1/100th as intense, we can subtract 20 decibels, and we get 50 decibels as the answer. So we're 10 times further away. The effective area is increased by 100, so we're decreasing the intensity by a factor of 100, or 20 decibels. Now, sometimes we talk about loudness, and loudness is different than decibel levels. Sound intensity is objective. We can measure that. Loudness depends on who's talking. Loudness depends on who's listening. And our perception of what is loud will change with frequency. I mentioned earlier the hair cells. They're not exactly hair cells, but they're groups of cells called cilia in the cochlea of our ear. High intensity sound waves can actually damage those. And what level of intensity will damage the cilia really depends on how long of an exposure you get. So 110 decibels, if you're exposed to it for more than a minute, and that's a level of a rock concert, you can risk permanent hearing damage. A jackhammer, 100 decibels for more than 15 minutes, you can risk permanent hearing damage. But here's the troubling one. Prolonged exposure to any noise above 85 decibels can cause gradual hearing loss. And most MP3 players can easily achieve noise levels much higher than that. And so if we don't turn down the sound on our phones, on our iPods, we run the risk of hearing damage. What makes it even worse is earbud headphones. They don't filter out external sounds, and so they tend to make us want to turn it up in order to be able to hear the music over background noise, and they're positioned very close to the eardrum. And since intensity equals power over area, the closeness of those can be very dangerous for our ears. Okay, so that's sound intensity. I think that's enough for today. Please go ahead and work your way through the worksheet, and we'll talk about interference tomorrow. Have a great night.